Hi, this is Shel Gunneman, and I'm here to talk to you about how science is storming the cloud. This is a new paper we have out in AGU Advances, and I thought GHRSST would be a good place to talk about this because it affects a lot of the satellite data processing that we're doing within GHRSST. So I'm going to sort of explain or talk about where we're at and where we're going. And so science, I see it really stands at the cusp of a new open science cloud-enabled era. Advances in data, software, and computing are enabling transformational interdisciplinary science, and they're really changing the realm of possible questions. Deliberately designed open science communities can advance science and inclusivity simultaneously. And so how do we as scientists and the institutions that we're at and the agencies that we work for better enable participation in these open science activities for this inevitable transformation? So first, I'm going to break this down into sort of data, software, and computers. And data, as we know, it's the current model is to bring the data to you. You download it, or if you're lucky and it's not a huge amount of data, you can get it via OpenDAP, so some sort of online protocol. But some of the really big data sets can take months to download, like CMIP6. And then once you come out with a new version, or even the MR-SST, which is like 4 terabytes, then you need to download it again. And then you have storage and maintenance costs. And this discourages external collaborations because in order for them to reproduce your results, they have to download and do all those steps to get the data into their local infrastructure. And this sort of reinforces institutional advantages where large institutions can sort of afford for someone to create local archive centers, local data centers, and maintain them. So there's also software, right? That's what we write all of our programs with. And in the science world, this is where lots of people are still using closed software. And closed software results in redundant efforts. Everyone is writing the same reader for that netcdf file over and over again. It also can be more error prone because there's less eyes on it. And it impedes advancements because all that time you spend with those redundant efforts is time that you're not spending just starting where somebody left off and building new extensions on. It's difficult to share software and its version control. You email it to somebody, but then if you discover an error, you have to try and remember who you emailed it to, and they don't know how to credit you because there's no DOI on the software. And this again reinforces institutional advantages where if somebody's at the same institute, maybe they have access to some of your software. And also, once you've built the software for that institute, they can continue to use it. We also have local infrastructure where we do most of our analyses. And a lot of times this is run on compiler-specific operating systems in unique environments that you have to learn with each institute that you move to. And there's software restrictions. So sometimes you can't use some software on one OS, but you can use it on another OS. And again, like this reinforces institutional advantages. It's for people outside of institutions who have to manage their own compilers and manage their own environments. Sometimes they don't have the expertise to do that. When we publish, sometimes we publish in paywalled journals, and this can restrict access to knowledge and perpetuate exclusionary practices. Institutions often can negotiate reduced publication rates, reduced access rates for their employees and researchers. And so people outside of larger institutions have trouble accessing this knowledge. And you end up constantly emailing other scientists to get copies of their papers. All of this sort of taken together maybe changes a little bit how we get solutions. So like we can get solutions, but if everyone's trained in the same way or everyone goes to similar institutions, is it the best solution? And so here's just some examples, like heart valves and seat belts are made to only fit men's bodies because that was the testing that they use. And there's no question that heart valves and seat belts have made humanity better and safer and we live longer, but they're not as good for women. And Twitter and Zoom, their AI racial image cropping has this algorithm bias against dark skins. And voice recognition software only recognizes the voices of men. I find this when I use my cell phone. I find this when I use AI to make transcripts of talks. So these are all solutions that, they work, but they don't work for everyone. And one of the things that is really important is, as we're moving towards open science, that we try to broaden participation in science so that the answers that we get are actually better answers. Because there's more voices, there's more people in the room. And a lot of this has been enabled now with the open science community. I mean, the technology, we can work together and make them possible. The steady advancement of open source technologies have suddenly removed barriers to collaborations. And this isn't a specific sudden breakthrough, but instead it's been the result of steady, consistent open source developers addressing the needs of the community. And these open science projects have more connections and they include more people amplifying their impacts. And it's been demonstrated by research and also my direct experience that open projects build more connections and include more people to solve problems. We get better results. And so how does this all sort of come together? This comes together with someone, a user, and through a web browser, I can either authenticate myself on a remote computer or just use my local computer. It's just one more authentication procedure. Once I've done that, I have access to a Jupyter Lab environment, a Jupyter notebook, and that can be running on my local computer. So it can be on-prem, it can be on an HPC, or it can be on a cloud. It's almost invisible to me because the environment that I'm encountering looks the same to me no matter where it's located. And this environment is populated with, like, hopefully all my favorite software libraries. And the interface I use is notebooks or Python. This connects on the back end to a server farm on the cloud, if you're on a cloud or HPC. And that server farm is adjacent to vast data stores. So now for the first time, I can open up a web browser window and in a couple of clicks, I can access petabytes of data, hundreds of computers, scale my analysis. And this is really powerful for doing open science because it allows me to share my environment and my coding with others so that we can collaborate together very efficiently. And so this is the new world. This is open data. We have cloud-based data so that everyone has access to it. Most of the large providers are negotiating for free egress. So you're not paying to access the data and you can download it for free. It's much easier to collaborate when everyone has access to the same data. And it's easier to reproduce and build on other people's results. And the access isn't bandwidth limited. And there's more interdisciplinary research because no longer are you siloed into these domain-specific archives. The data for all of the different domains are all available at the same cloud server. And they may not be in the same region, but most of them, the region is pretty invisible to you. And this is going to broaden participation in science because more people will have access to these vast data stores that previously were only available for large institutions. So what do we do about software? So software, if we do open software, it can be permissively licensed so other people can build on it. It's public on GitHub, which makes it really easy to share your code and collaborate with others, do version controls, get a DOI for your code when you publish it. And you can collaboratively build tools. Now, this leads to more robust code. And this has been the increase in AI and ML. There's just this massive explosion in science with the use of really advanced analytical tools because of open source AI and ML toolboxes that have made building these models just a few lines of code. And this speeds up science substantially. When I can open any file that I want that's netcdf, and I can build a machine learning model in a few lines of code, this speeds up science because I'm not constantly rewriting all of these little bits of code to read and to process and to filter data. We're doing it together. And this is this same vision of this user going through a browser to authenticate. and access a server farm with stores of data. These are these Jupyter hubs or these platform agnostic open source software infrastructure solutions. And this is where we bring this all together. It doesn't matter where it's located, and it's developed by the community, and it's rapidly becoming the default for science. And one of the things that we're really going to struggle with, I think, in the next couple of years is, what does this look like as scientists need access to this? And we want to really make sure as scientists that we're vocal here so that we don't get a government imposing a solution on us, and that we continue to advocate for these open source platform agnostic solutions that are probably going to be different and look a little different with different environments for all these different groups. But we need to keep contributing to the open source projects so that we all grow together. And this is what we get if we do this well. We get a supercomputer behind every device, and that breaks down the institutional advantage and opens access to science for more people to participate. In this lower left-hand corner, I have a Raspberry Pi. It's a $36 computer, and I'm running over 80 workers with almost 250 gigabytes and processing CMIP6 data. And on the left is on AWS, and on the right is on GCP. You could do this on the airplane, you can do this on the train. It's just pretty amazing. It's just through a browser window. And that means that even if I have intermittent power and low bandwidth, I can power up a laptop or a cell phone, upload my code, start workers, start computation, and then even if I'm interrupted, that's okay. My computation keeps going. And so we're working to sort of identify what barriers are there, like what barriers to data. Are they on the cloud yet? Are they easily accessible? What's your software release policy? And these are things that as scientists, we're going to have to worry about, and we should be vocal about making sure that they meet our needs. What's the software release policy for your institution? What's your GitHub policy? Your repository permission policy? How will your agency enable access to these resources? And I want to end by saying, like, it's really important that we design this community as we start to move towards it to incentivize openness. We can design a more inclusive community that makes science better and faster. And we want to highlight early successes on the way to that transition and coordinate and move together. And I'm going to end with just showing, these are linked slides. So this is some of the ways that we can do this. There's a lot of online resources. Moving towards openness, it's not a closed and open binary thing. There's a spectrum of openness for data, for software, for computations, for reproducible science. And the Turing Way, OpenScapes, the Carpentries, our paper and AGU advances, they all discuss and provide a lot of resources for helping scientists to do this. So thank you.